Hello everyone and welcome to lecture. Today we're going to be talking about specifically what are called traces of multivariable expressions, and we're going to be using these to define level curves and actually level surfaces of functions of multiple variables. So what is a trace? That's the first thing we have to define. And I'll write down the definition in words, and then we'll kind of go through and see a couple different examples. So the trace of a multivariable expression is the curve or surface that results when one of the values in the expression is fixed. So it's sort of like a cut or a snapshot of the expression with one of the values in the expression fixed at some number, some specific fixed value. And the main idea that we're going to be using this for is to help us visualize the expression without the use of a graphing software. So we can use to help us visualize the expression geometrically. Specifically, they help us visualize exactly, so they show exactly what curve or surface the expression represents. So let's see a couple examples. We'll start with some simpler examples and move on to more complicated examples a little bit later on. So we'll start with the example z is equal to x squared plus y squared. Now if you open up Geogebra and type this into Geogebra, it'll actually give you the surface that is represented by this relationship right here. But this relationship is saying that we want all points x, y, and z, where z is equal to the function x squared plus y squared. So f of x, y here is the function of two variables, x squared plus y squared. So before we do that, before we open up Geogebra, we want to kind of take a look at the traces of this function and see if we can figure out what this is going to look like before using Geogebra, to kind of get an idea of how to do this without even using a graphing calculator. So there's going to be three traces to this expression right here, because we have three variables in this expression. There's going to be an x trace, there's going to be a y trace, and there's going to be a z-trace. So the x-trace is what we get when we fix various values of x. So like fix x equals c, say, and when we do this, we get the equation z is equal to c squared plus y squared. So if x is fixed at various values of c, this is going to be, you want to think about what type of curve this is going to be for various values of c. And you could even, if you want to, you can make a table where in the table you put a column for the various values of c. I'll do 3 separate values of c. So the expression that you get is z is equal to c squared plus y squared. And when c is -1, you get z is equal to -1 squared, which is just 1, plus y squared. When c is equal to 0, you get z is equal to 0 squared plus y squared, which is z is equal to y squared. And when c is equal to +1, you get z is equal to 1 squared plus y squared, which is just 1 plus y squared. And what you can do is you can then take each one of these cross sections, so you see that each one of these things is a function in the zy plane. So where you have z is this axis right here, and y is this axis right here. Well, when c equals 0, you get z equals y squared, so that corresponds to a parabola in the zy plane. Z equals y squared corresponds to c equals 0. And then both when c equals -1 and when c equals +1, you get a parabola that's looks very similar, but it's shifted up by 1. So this corresponds to c equals -1 and c equals +1. And if you do this for other values of x or other values of c, so if you fix x at other values of c, you're going to get other parabolas. So you do the same thing for the y-trace. You fix values y equals c. It's going to be a fixed c value. You get the equation z is equal to x squared plus c squared. And the table that you get is going to be very, very similar to the table that we got for the x-trace. It's not always very similar, but for this function, it's kind of nice. It's relatively symmetric. So when c is -1, 0, and 1, we're plotting here with y fixed, so it's going to be x squared plus c squared. So when c is -1, you get z is equal to x squared plus 1. You get, when c is 0, you get z is equal to x squared. When c is equal to +1, you get z is equal to x squared plus 1. And if we visualize this, this is now going to be in the x. We're fixing values of y, so these traces are going to be in the xz plane. When c is 0, you get z equals x squared, which is this parabola right here. And then again, just like before, when c is equal to 1 or when c is equal to -1, you get the parabola x squared plus 1. So the last trace that we have to do here is the z trace. The z trace, just like the other two, is going to be when we fix the value of z equal to x squared plus y squared. Oh, sorry, we fix the value of z equals c, which gives us that c is equal to x squared plus y squared. So the expression that we have here is that x squared plus y squared is equal to c. This is the trace that we get when we fix z. And let's look at it. So we aren't going to have any negative values of c because there's no way of taking two real numbers, squaring both of them, and adding them together to get a negative value. But we will get c equals 0, x squared plus y squared equals 0. There's actually only one point that satisfies this relationship, or this expression. That's the origin. That's when x equals 0 and y equals 0. C could be equal to 1, say, in which case x squared plus y squared is equal to 1. It's the equation of a circle of radius 1. If c is equal to 4, then x squared plus y squared is going to be equal to 4, which is the circle of radius 2, and so on and so forth. So you can pick any positive value for c and get a circle. It's going to be the radius of which is going to be the square root of c. And what this means in terms of our level, these are actually the level curves of this function. We'll see that a little bit shortly. But the z trace here is exactly going to be the point. So the origin point here. Right, this corresponds to c equals 0. And then we have a series of concentric circles for our other traces. And make that a little bit bigger. So that origin point corresponds to c equals 0. This circle right here has radius 1. Right, and that corresponds to c equals 1. And then the circle of radius 2. Corresponds to c equals 2. So you see here the circle of radius 2 corresponds to, not c equals 2, sorry, that was a typo. It corresponds to c equals 4. And for any other value of c, you have a circle is the trace of this expression, the expression z equals x squared plus y squared, in the z along the z-axis. So we can use these in order to visualize what this surface is in 3D. You use these three traces to do this visualization, specifically. If we have our three axes right here, our x-axis, our y-axis, and our z-axis, and we want to visualize the the surface given by z is equal to the function x squared plus y squared, well, along the fixed values of x, specifically fixed value of x equals 0, we have this parabola right here. Kind of opening up along the x-axis, that's this parabola. When y is fixed at 0, you have a parabola that opens like this along the y-axis. It's this parabola right here. And then for any fixed value of z, you have circles of varying radii. So for any fixed value of z, you have these circles. And you can hopefully see that this is in 3D, what's called a paraboloid. Right? Or a parabolic bowl. And in office hours, we've seen that this shape is very clear. And we can also add, I'll open up Geogebra right now just to show that this is exactly what you get. So we can clearly see that, and this is the exact shape that we get. And we don't even need Geogebra to figure out what this three-dimensional shape is. If you just argue based on those traces that we did, specifically, I'll do 3 of the traces right here just so you can see them. So the first trace we did was z equals just x squared, which is exactly this curve right here. That second trace that we showed was z equals y squared, which is the parabola along the y-axis. So it's this curve right here, the intersection right here. And then the last trace is just do x squared plus y squared equals 1. You can do any c value, any positive c value, but x squared plus y squared is equal to 1. Corresponds to color a different color. So you can see the intersection of this circle right here is a circle of radius 1. That's where the paraboloid intersects, is along a circle of radius 1. And you can see even more specifically, if you end up going through and kind of doing other traces, so if you consider all of the traces of the function, that's probably the best way of seeing that. So the idea here is that this is a very good example. It's a relatively simple example, but it's a great example for really understanding what a trace is and why traces are useful. Let's do this again for, another relatively simple example, but it's going to be an example that it's a little bit different than x squared plus y squared, and it's going to generate a completely different shape. So we'll do the example z is equal to x squared minus y squared. So sure enough, we want to do all of our traces here. We want to do the x trace, the y trace, and the z trace. So for the x trace, we're fixing values of x. For the y trace, we're fixing values of y. And for the z trace, we're fixing values of c. And when we fix values of x, we get the relationship z is equal to c squared minus y squared. When we fix values of y, we get the equation z is equal to x squared minus c squared. And when we fix values of z, we get c is equal to x squared minus y squared. So just like before, for each one of these cases, we can make a table, and that table is going to tell us everything we need to know regarding what this curve is for this trace. Say c, well here we'll do c equals -1, 0, and 1. So when c is -1, we get z is equal to 1 minus y squared. When c is 0, we get z is equal to 0 minus y squared, or negative y squared. And when c is equal to 1, we again get z is equal to 1 minus y squared. For the y trace, we have a similar table. We get z is equal to x squared minus 1. We plug in -1 in for c here. Z is equal to x squared, and then again z is equal to x squared minus 1 when 1 gets plugged in for c. And lastly, for the z trace, we have the curves x squared minus y squared is equal to -1, x squared minus y squared is equal to 0, and x squared minus y squared is equal to +1. Those three curves are the traces corresponding to each individual value of c for this function. So let's look at, in each individual case, what these traces are. Just like before, for the x trace, we have curves in the zy plane. So we have curves the y-axis right here. This is the z-axis. And specifically, we have curves that at c equals 0. So when x equals 0, the intersection is this curve right here. It's a parabola opening down. The parabola z equals -y squared. And when c equals both -1 and +1, we also have a parabola opening down, but shifted up by 1. Alright, so this corresponds to c equals 0, this corresponds to c equals 1, and c equals -1. And there are, for any other value of c, you're going to have a parabola that's opening down like that. Similarly, the y traces again are going to be in the zx plane. And we have that when c equals 0, the trace is the expression z equals x squared. And when c equals 1, we can have this with 1, and when c equals -1 as well, we have an upward opening parabola. Oh, and sorry, this should be shifted down by 1 because you have a -1 right there. Oh, it's going in the slightly wrong direction right here. So there you have it. These are the traces in the y traces, the traces in the zx plane, and the collection of all of these for every single c gives us the traces of our function or our expression. And the last traces here that we have to consider, and these are definitely the most interesting for this expression, are the z traces for this expression. And these traces are in the xy plane. And what we want to look at is exactly what each one of these is. So we'll look at c equals 0 first. In c equals 0, we have the equation x squared minus y squared is equal to 0, which is the same thing as the equation x squared is equal to y squared, or the equation, if I take the square root of both sides, the square root of x squared is equal to the square root of y squared, which is that the absolute value of x is equal to the absolute value of y. And specifically what that gives me then is the curve y equals positive x and the curve y equals negative x. So all of these points, all of the points that are on here satisfies c equals 0. This is the cut of this surface when z equals 0. And the other two curves are actually the defining relationships for what are called hyperbolas. So for c equals positive 1, the equation x squared minus y squared equals 1 is actually a hyperbola that's opening along the x-axis, so it looks kind of like this. And same thing right here. So this corresponds to c equals 1, c equals 1. C equals 1 on this curve and on this curve, because this is the hyperbola, or it's called the unit hyperbola. I'll do a similar hyperbola right here. I'm going to put a dotted line just to denote that this hyperbola is the hyperbola where c equals negative 1. Or it's the trace when c equals negative 1. And so the combination of these pictures gives us a very, very nice picture of what our surface is going to be looking like in 3D. And It's a little bit harder to visualize than before, but it's definitely possible to do. You're going to have that in the ZY plane, you're going to have parabolas that are opening down, or you're getting less and less in this direction right here. And you're going to have in the ZX plane, you're going to have parabolas that are opening up, but getting lower and lower and lower. So it turns out that this shape has a very, very nice name. It's what's called a saddle. So if you've ever been horseback riding, or if you've ever been hungry and wanted some Pringle chips, right, the Pringle shape is exactly the saddle shape. And we've seen from the traces that we have that exact saddle in terms of just the traces themselves. We kind of predict that using the traces of this function. But if we open up Geogebra again and take a look at this, we can see this directly. So this is exactly the shape that we're talking about, and we just described using only the level surfaces. It's exactly that saddle shape. And you can very clearly see that for any fixed value of, say, z, there's z equals 1. You get that the intersection of the z equals 1 with the value of the surface is in fact a hyperbola. It's the unit hyperbola opening along the x-axis, just like we saw. And for any fixed value of, say, we'll do a fixed value of y, like y equals 1, and we'll color that a different color. We'll make it purple. So when y equals 1, you have a parabola that's opening up and shifted down by 1. That's exactly that intersection right there. And that matches the traces that we calculated earlier. So the idea here is that you don't actually need GeoGebra or a 3D graphing calculator to visualize these things, but it certainly makes it nice to verify the work that you're doing and to understand a given relationship that you have. So to visualize this for any other quadric form, because there's many other types of quadric forms, we have in our book, and also I'll post a sheet of all of the quadric forms and the surfaces they represent. So as you can see right here in this sheet, we open it up. We have a list of all of the various quadric forms and the surfaces that you get when you look at those quadric forms. So we have an ellipsoid, an elliptic paraboloid, hyperbolic paraboloid, and so on and so forth. In order to figure out what the shape is without using GeoGebra or an online or a computational tool, you would use this method of traces that I just went over. So it'd be a good idea to take some of these expressions and use the method of traces to verify that these are the correct shapes that you get. But you see that there are many different types of quadric surfaces. There are an elliptic cone or a cone, an elliptic cylinder, a hyperbolic cylinder, the hyperbolic paraboloid that we just did, the elliptic paraboloid that we did in the example before. But each one of these expressions mathematically is given by a quadratic combinations of sums of the x, y, and z coordinate. And this is a kind of a summary sheet that I'll post and you can use. It'll also be in your calculus book, your multivariable calculus book, and you can use to help you identify quadric surfaces. And we've already seen that this is a very, very useful tool for visualizing how a function is behaving. Specifically, the next part of lecture, we're going to see that the main reason we're interested in these quadratic surfaces is because they help us talk about the level curves and the level surfaces of three variable functions. So the level curves of two variable functions and the level surfaces produced by three variable functions. So we'll start with level curves, and these are defined for functions of two variables. And the main description is that this is that they're a tool for helping visualize a relationship of the form z equals f of xy. Specifically, the level curves for a function of two variables are the trace when you fix values of z. And the picture that you want to have in your mind when you're doing this and you're kind of thinking of this is the following. So we've seen that functions of two variables, or a function of x and y, can be visualized by looking at the graph of the function, which in general is going to be a surface over some domain. So the value of the function might be this value, this value, this value, and this value at the corner points. Maybe the function looks like this. Okay, this is our surface z equals f of xy. Let's say maybe it has a maximum value, just so that we can kind of better get a sense of this drawing. Say it has a maximum value at, say, this point right here. The surface maybe comes down like this. Maybe it goes up to a maximum value and then down to the boundary right here. So the idea is that the level curve generated by a given, fixing of the z coordinate, if we say fix z at some z value, is the curve that we get when we consider the intersection of this surface intersecting a fixed z value. So let's say we fix z equal to c right here, where c is this value, this fixed value right here. The intersection of the surface with this z value maybe looks like this. Now, this could be the level curve of this intersection, and this curve is called the level curve of the function. You can visualize moving this c value up or down and the curve of intersection is the level curve of the function. So if you consider multiple different level curves of the function, you get a visualization of how this function is getting larger or smaller in the plane, in the, as you move around the plane, the domain space of this function. This is the same thing as what's called a topographical map. So if you've ever been hiking before, right, the level curves of a function of two variables are the exact same thing as a topographical map. Specifically, the topographical map that you're interested in when you're hiking is the height of the function at any given point. So the level curves on the topographical map give you the height of the mountain or the trail that you're on while you're hiking at any given point on the topographical map. But the idea is that we can do this for any function, no matter what the function is, and use this to visualize the level curves of our function. We'll look at a couple of examples. Look at the function z is equal to e to the negative x squared plus y squared. So the level curves of this function are given by fixing z equal to c. And when we do this, we get the equation e to the negative x squared plus y squared is equal to c, which we can rewrite by taking the natural log of both sides. If I take the natural log of the left-hand side, I get negative x squared plus y squared is equal to the natural log of c, and then this gives us that x squared plus y squared, if we multiply both sides by negative 1, is equal to negative the natural log of c. And remember that x squared plus y squared is the same thing as r squared. So the level curves of this function are circles of a radius square root negative natural log of c. And what's nice about this method is that looking for the level curves of a function of two variables directly gives you the actual range of the function, because the range of the function is all of the values that can be hit by the function. These are all possible values of c for our function. The range of f is all possible values of c. And so if we look at this example, we see that, well, the natural log function is only defined when c is between 0 and infinity, because this tells you that c can only be between 0 and infinity. And we also need to enforce that this square root right here has to be defined for the radius. It has to be a positive square root. So this only works when the thing under the natural log, or this negative ln of c, is greater than or equal to 0. Which means that ln of c has to be greater than or equal to 0. If you, ln of c has to be strictly less than 0. If you multiply this inequality by negative 1, you get that the inequality flips over, and you have to have that net ln of c is less than 0. And what that means then is that c, if you look at the graph of the natural log function, if the natural log function is a function of c is less than or equal to 0, that means that c has to be between 0 and 1. So what we see is that this gives us a restriction for c, that if the natural log of c has to be less than or equal to 0, then c has to be between 0 and 1. And this exactly gives us the correct range of our function, because the range of the function is all possible values of c. So the range of the function here is equal to the open interval at 0 and the closed interval at 1, where we have exactly what we've just shown, that the range is equal to this interval from 0 to 1, or the set of points where c is between 0 and 1. And we can look at this and kind of go through. If you do the traces of this function, you'll see that the traces exactly look very similar to the function. So the y trace when y equals 0 is the function z equals e to the negative x squared. The x trace, these are just the traces at 0, but sometimes that's enough to give you an idea of the shape, is e to the negative y squared. And this is the function z equals e to the negative x squared. And along the y-axis, you also have this same shape. It's the function z equals e to the negative y squared. And if you do the traces along z, or the level curves of this function, you'll see that the level curves are all circles. Which is why this function is sometimes called a bump function. It's like a bump at the origin. So if we open up our Geogebra window, this is exactly what we'll see. Here's z equals e to the negative x squared minus y squared. And you can hopefully see very clearly now that this is exactly the shape that we get. We get this bump shape, which is the function e to the negative x squared plus y squared. So this method of traces is a very good method of visualizing, and we can see very clearly that the level curves of this function are exactly what we would expect. So the range is exactly what we would expect, and if we view the level curves of this function using either Desmos or Geogebra, I'll probably use Desmos right here. the level curves of this function look like the following. This is for C from 0 to 1. So the level curves of this function are exactly circles. So for any given value of C, we have that the level curve is a circle. So this is a pretty powerful tool for us in terms of visualizing multivariable functions. The next example that we can consider for our topographical map in level curves is look at the function w, say is our output, is equal to sine of pi over 2 times x squared minus y squared. To find the level curves, the topographical curves, we fix w equal to c, which gives us the equation that our function, this is our function in this case, is sine of pi over 2 times x squared minus y squared. And if that is fixed at some c value, then we can actually solve for c. Right? This is going to be, or I should say, solve for x squared minus y squared here. Think of the shape of these level curves. If we take the inverse sine function, arc sine of both sides, we get pi over 2 times x squared minus y squared is equal to arc sine of c, which gives us the equation x squared minus y squared is equal to 2 over pi times arc sine of c. And this is the algebraic equation of the level curves for this function, which means for various values of c in the range of this function, we have the level curves are given by curves of the form x squared minus y squared is equal to some k value, where this k is 2 over pi times the arc sine of c. So curves of this form are hyperbolas, like we talked about before. And so what that means is that the level curves of this function are exactly going to be hyperbolas. For various values of c. And specifically, they're going to be changing with the value of c that the function is. So these curves, these level curves, are giving us the value of the function, the c value of the function for every single possible value of c. So again, if we open up a plotting window, try and visualize this, we can do just that. You go in and visualize this function, sine of pi over 2 times x squared minus y squared. You can see that this is exactly what we're getting. We're getting the function has level curves, which are hyperbolas, and it's like a sine function going up and down, up and down, up and down on these hyperbolas. This is directly verified by looking in Desmos as well. If you kind of go into Desmos, and you can also do the level curves in GeoGebra by fixing a given plane. So if you want to say fix the z value of, we'll say z equals 0.7. The level curves at z equals 0.7 are all of the intersection curves of this plane right here, which is z equals 0.7 with the surface itself. But Desmos will give you a slightly nicer plot of just the curves themselves, the level curves themselves, if you kind of go through. And you can also do a slider. You can do a slider in both GeoGebra and in Desmos. But if we do sine of pi over 2 times x squared minus y squared, equals c, and we'll go from -1 to 1 because that's the range of this function. You can see a clear plot of the level curves of this function. And the level curves of this function are exactly hyperbolas. And as you move along, around to the level curves are changing on these hyperbolas. So for instance, these curves are the level curves for c equals -0.5. If you change c to 0.2, the level curves change. So these right here are the level curves for c equals 0.02. But the idea is that this is how we visualize these functions of two variables. And you'll notice that this visualization is only, we're visualizing a function of two variables inside the two-dimensional space that you're in. So this is a very, very useful tool for us in terms of helping us figure out what a function of 2D is looking like inside its domain space. So a natural question to ask is, can we extend this idea to functions of three variables? And the answer is exactly yes, we can. Specifically, this is done using what's called a level surface. Level surface is like a level curve, but for a function of three variables. Specifically, if we have a function of three variables, f of x, y, z, we say that the level surface of this function of three variables is what happens when, so the output is w and the function is a function of three variables, f of x, y, z. The level surface is what you get when you fix w equal to c for some fixed c value, and you consider the set of points x, y, and z that satisfies f of x, y, z is equal to c. The set of all points that satisfies this relationship the set of all points x, y, z that satisfies f of x, y, z equals c is called the level surface of the function f corresponding to the value c. So there are a number of different examples that we can go over of a function like this, or a level surface for a function like this. But I'll do a similar one to before, where f of x, y, z is equal to, we'll say, e to the negative x squared minus y squared minus z squared. The level surface for this function is going to be the following. It's going to be, well, we fix w equal to c, and we get that e to the negative x squared plus y squared plus z squared is equal to c. So we can take the natural log of both sides. And so we have then that x squared plus y squared plus z squared is equal to negative natural log of c. If you remember that x squared plus y squared plus z squared is rho squared, or the distance from the origin squared, that means that the level surfaces for this function of three variables are going to be spheres of radius rho, all given by having the square root of negative natural log of c exists. So this expression gives you the range of the function. You can do it using exactly the same calculation that we did before, but if we open up Python now and show a visualization using my plotting program for 3D functions, we can see a direct visualization of this. So this right here is the output of the Python graphing program that I wrote in Python, my custom Python code. And you can see that if we rotate this around, this is exactly a picture of this function, e to the negative x squared plus y squared. So you see that the level curves are definitely spherical. If you fix any value of the function, you get a sphere around the origin for that value of the function. The maximum value of the function is 1. Right here, and I haven't plotted all points because the domain of the function is all values of x, y, and z, but as you move away from the origin, the value is getting closer and closer and closer to 0 at the minimum value of the function. So this is a pretty cool thing. You know, these level surfaces allow us to visualize and understand how a function of three variables is changing with respect to moving around in space, which is a very important thing for things like temperature, mass density, really, you know, the electromagnetic field, really any physical example you could think of, really is a function of variables, three variables in space, and possibly more variables like time. It could also be changing with respect to time. Let's do one more example. Maybe we'll do 2 more examples, we'll see. We'll do f of x, y, z is equal to cosine of pi times the square root of x squared plus y squared plus z squared minus 1. So to find the level surfaces, we fix w equals c, and then we look at the equation that we have here, which is cosine of pi times the square root of x squared plus y squared plus z squared minus 1 equals this fixed value of c. And if we kind of try to simplify this a little bit, we take the arc cosine of both sides to get pi times the square root of x squared plus y squared plus z squared minus 1 is equal to arc cosine or inverse cosine of c. And we divide by pi and square both sides to get that x squared plus y squared plus z squared minus 1 is equal to 1 over pi times arc cosine of c squared. And lastly, if I add 1 to both sides, I have x squared plus y squared plus z squared is equal to 1 plus 1 over pi arc cosine of c squared. Remember, x squared plus y squared plus z squared is equal to rho squared. So what this means is that the level surfaces of this function are spheres of radius rho is equal to the square root of 1 plus 1 over pi arc cosine of c squared. That's what the level surfaces are. They're spheres of these varying radii. So you can use Desmos to plot this out if you want to see what these level surfaces look like. But I'm just going to open up my Python plot and change the function to this function so we can kind of see what this looks like. So this is the Python output for this function. And it's a little bit unclear at first, but if we kind of rotate this plot around a little bit, we can see that this is exactly what we have, that there's level surfaces here that are spheres. So the spheres are the constant levels, and as we move away from the origin, we're getting like a cosine behavior, where near the origin we're close to 1, and we move away from the origin a little bit, and we're close to -1, and so on and so forth, going up and down on spheres as we move away from the origin. It's a little bit hard to see with just the basic plotting capabilities of Python, but it's exactly what's happening. As you move away from the origin, it's the cosine function, which exactly matches up with what we expect from this function itself. If you look at the function here that we're looking at, which is cosine of pi times the square root of x squared plus y squared plus z squared minus 1. This is a very powerful tool here. It's a tool for helping us visualize what a multivariable function looks like. And I'm going to end the lecture here. You can do many other examples, and I can definitely talk about more examples in the future, but this will end the lecture for today because I've described the concept of a trace, and I've also went over level curves for functions of 2 variables and level surfaces for functions of 3 variables. So I hope you all have a great day today, and I hope you learned something. But have a great day, and I'll see you next lecture.